In any Excel models where inputs lead to outputs through Excel formulas, sensitivity analysis is a key aspect of the overall modeling process. Its goals are typically to see how variation in the inputs affects the outputs, and to see which inputs have the largest effects on the outputs. Sensitivity analysis applies to simulation models just as well as it does to other Excel models, and At-Risk provides several tools to implement sensitivity analysis. These tools are illustrated in this video. The model of discounted cash flows you see here is used for illustration. This model is adapted from one of the At-Risk example files. The uncertain inputs appear in green font, and the single At-Risk output, NPV, appears in maroon font. Sensitivity analysis can be performed only after a simulation has been run, so the first step is to run the simulation. After running it, you see the distribution of the NPV output. Then a very simple sensitivity analysis is to click the sensitivity button, the one with the icon that looks like a tornado. This provides the following options: 4 possible tornado graphs, a spider graph, and various settings. The purpose of each of the graphs is to show how the NPV varies as the uncertain inputs vary. The first tornado graph option returns the following graph. It shows how the mean NPV varies as each uncertain input varies over its range. The bars are shown in decreasing order of their lengths, from top to bottom, so that the inputs at the top are those with the largest effect on mean NPV. Of course, this shape is where the tornado graph gets its name. Clearly, the annual revenue growth rate has the largest effect. If you would rather see how a percentile of the NPV distribution, rather than the mean, is affected by the inputs, you can choose the Settings option and fill in the dialog box as shown here. Change this to percentile, and change this to the percentile you want. The tornado graph changes as you see. But again, the annual revenue growth rate has by far the greatest effect on the 5th percentile of NPV. For the remaining graphs, I will change the setting back to mean NPV. The other 3 tornado graph options show similar results in slightly different ways. The first option shows the regression coefficients if the 5,000 NPV output values were regressed on the 5,000 sets of input values. For the second option, regression map values, the length of each bar is the amount of change in NPV due to a 1 standard deviation change in the input, holding the other inputs constant. The third option, correlation coefficients, shows the Spearman rank correlation coefficients of NPV versus each of the inputs. Finally, the spider graph option provides a line or curve that shows how mean NPV changes as each input varies through its percentiles. Again, this shows that the annual revenue growth rate has the largest effect on mean NPV because its line is the steepest. These same options are available in the summary window by clicking the second button from the left. Also, a tornado graph appears in the output worksheet when you ask for quick reports from the Excel Reports button. Finally, the information is available in a handy interactive format by clicking the Simulation Sensitivities button, again the one with the tornado icon, in the Results group of the At-Risk ribbon. The drop-down lists at the top and the buttons at the bottom provide plenty of options that are quite self-explanatory. For example, the middle button at the bottom, the one that is currently selected, lets you see a scatter plot of NPV versus each of the various inputs. And you can double-click any of these to get a larger view, such as this one. The blue and green coloring is for the lower and upper 10 percentiles of the input variable, and numbers in the colored boxes indicate the percentages of points in the 4 quadrants. This is a lot of information for very little work. Actually, you can create this type of scatter plot directly from any of the tornado graphs discussed earlier. You simply drag any of the bars on the tornado graph off the window and you automatically get a scatter plot of the output versus that input. There it is. Finally, At-Risk has an Advanced Sensitivity Analysis option under the Advanced Analyses dropdown on its ribbon. When you choose it, you see this dialog box where you can select an output cell to monitor. I will monitor NPV, and you can click Add to add inputs to vary. I will fill in the dialog box for one possible input to vary, the annual revenue growth rate. This is an uncertain input, so its type is distribution. And I will let it vary over 7 representative percentiles. Next, I will fill in the dialog box for another possible input to vary, the discount rate. This is a fixed input, so its type must be cell, and I will let it vary over 7 percentage changes from its base value of 0.12. Once you have added as many inputs to vary as you would like, you can click the Options button to select the graphs and other report options you want. I'll keep those. Then you can click the Analyze button to run the analysis. At-Risk will run a separate simulation for each value of each input being varied. In the present case, there are 7 percentiles for the annual revenue growth rate and 7 percentage changes for the discount rate, so At-Risk will run 14 simulations. For example, for the first 7 simulations, the annual revenue growth rate will be fixed at each of its 7 percentiles. The discount rate will remain at its base value of 0.12, and the simulations will then run as usual. Of course, during these 7 simulations, the other uncertain inputs will vary according to their distributions. After running all of these simulations, At-Risk shows the results in numerical and graphical forms in new worksheets. There are the numbers, and here is the tornado graph. Obviously, the mean NPV is much more sensitive to the annual revenue growth rate than to the discount rate. As this video has shown, sensitivity analysis plays a very important role in At-Risk. Every time you run a simulation, there are handy buttons available to show how sensitive outputs are to various inputs.